So in this video, I will be trying to explain as quickly as possible what convolution is, because it's not that convoluted, right? So convolution is essentially just adding. It's just adding two functions through time in a specific way. So let's say, as an example, we want to find the convolution between a desired signal x of t and h of t. And h of t is our impulse. So our desired signal is given to us, we know it, and our impulse, well, that's just an impulse function, if you don't know, is just how the desired signal responds when you give it this flick, right? This very short flick that's, in fact, it's infinitely narrow in time. That's the whole definition of an impulse. And that's what it is. It's just an impulse. You just let the desired signal naturally respond. That it's its natural response, right? Think about it like that. And so with linearity, we can assume that a function in time is a, how do I explain this? A function in time can be broken up into its impulses, right? So let's say, so here in the convolution formula, we have x of tau multiplied by h of t minus tau with respect to tau. So what is tau, what is t? Tau is a variable in time, and t is also a variable in time, but the way I like to think about it is that tau is more kind of analogous to a discrete time, where we are interested in specific points, right? Specific points throughout the signal in time. And t, should I say, is more of the continuous version, because x of tau is just a single value. It's a constant, it's a scalar. However, h of t, should I say, or t minus tau, regardless, is a function. And that's a function, it's a continuous function through time. So if we have a graph, let's say, of x of t, and another one of h of t, the impulse, let's say we can define our x of t as just anything. It could be anything. Let's say a squiggle. Doesn't have to be a sinusoid, just a regular squiggle. And let's say its impulse, when I give it this flick that's infinitely narrow in time, let's say it produces a exponential graph, an exponential decay, let's say. So what is convolution? Well, in visual terms, convolution is just adding, you're just layering and adding each of the impulses at every specific point through time, from the start of the region of time you want to the end. Let's say it doesn't have to be from minus infinity to infinity. It can be from 0 to x, really, to 0 to anything. It could be anything, any range. So that is what convolution is. It's just adding the impulses through time. However, it is also scaled by what the desired function is at that specific point. That's literally it. So as an example, as a visual example, what we have is its impulse at time t equals 0, and again at time equals some arbitrary point, let's say t equals 1, some another arbitrary point again, but this time scaled, because here it's greater in y, and again at this point scaled again at this point, and at this. And so I think you can get the message I'm trying to drive home here, is that it's just adding these impulses through time and scaled by what the magnitude of the desired signal is at that time, whether it's 1 or 2 or whatever. It's just layering the same impulse function and scaled over and over and over and over and over again. And so the reason why it may look convoluted or just intuitively difficult to infer is because when you see its final product, the final convolution, it's difficult to sort of decipher where this function came from. You don't know if it could have come from a sine graph, you don't know its impulse. There's not much information that is transferred over just by looking at this final product. And so it could be anything, and there's a reason why it looks very, very, what's the word? Very weird, should I say, very eccentric. And that's because it could just take on any shape when you're given its impulse and a specific function through a given range. But that is what convolution is. It's just adding.